So far in our discussion of the second law of thermodynamics, we've talked about entropy in terms of heat transferred in a reversible process to or from a system divided by absolute temperature. If the, say, the molecular theory were to be overturned, say, tomorrow, and somebody were able to prove that molecules don't exist, thermodynamics would still be valid. So far in our development, we haven't introduced any particular model. These are just general things we're talking about. However, if you believe, and most scientists do, that matter is composed of atoms and molecules, then you can give a statistical interpretation of entropy. I'll just briefly introduce this at this part of the course, and then toward the end of the course we'll talk more about it in the topic statistical mechanics, or sometimes called statistical thermodynamics. But first, here's a preview. Okay, this is the important equation. S, that's the entropy, absolute entropy. That's just not entropy change, delta S, but that's the absolute entropy, is K log omega. All right, so let's define a few things here. K is the gas constant R divided by Avogadro's number. So essentially it's a molecular or an atomic gas constant. This is per mole, K will be per molecule. And omega is the number of ways a particular state of a system can be obtained. So if you have more than one way, or a lot of ways to determine or to obtain a system, then omega is large and the entropy will be large. As I said, there's going to be more about this in the third part of the course when we talk about statistical thermodynamics. So let's develop this idea a little in a little way. All right, let's take a particular volume, and let's divide this volume up into 4 areas. Let's call this A, B, C, and D. And now we're going to introduce the a molecular picture, the molecular model, and we have, say, 4 atoms, and we'll call this 1, 2, 3, 4. And now what we're going to do is to introduce some sort of constraint. That's typically what you do in statistical mechanics, is you have some constraint introduced into a system. So first of all, let's say that all atoms have to be in volume A. This, what we're leading up to, is that experiment we talked about last time where you have helium on one side and argon on the other, separated by a partition. If you remove the partition, then argon will diffuse into the helium space and the helium will diffuse in the argon space, and that always goes one direction. You never see argon collecting at one side of the container and helium on the other. All right, so let's make this constraint. All atoms have to be in a position A. So let's look at number of ways subject to that constraint. And again, what we're doing is looking at number of ways of getting a particular state of a system. All right, so we can put molecule 1, 2, 3, 4 in there. We can't put any molecules B, C, or D because they all have to be in A by this particular constraint. I guess I'm confusing 1 with 1. So just let's see, 1A. What else do we have here? I don't know. Let's call this something. All right. So how many ways can you get this state with all of them in A? Well, there's just one way to get that. You put everything in A. This means that the entropy S is K log of 0. Log of 1. I'm anticipating what the answer will be. Log 1, and log of 1 is 0. So the entropy, when everything is constrained to be in a particular volume, the entropy there is 0. Now, we don't have a symbol yet, but now let's say all atoms have to be in either A or B. So now we're increasing the volume available for these 1, 2, 3, and 4 labeled atoms, we can now be in A and B. All right, so let's go ahead and do that. Let's keep track of the number of ways we can get this. A, B, C, and D. Well, we can have molecule 1 and 2 in A and 3 and 4 in B, and of course we're constraining them. They can't be in C or D. We can put molecule 1 and 3 in A and 2 and 4 in B. We've got molecule 1 and 4 here, and then 2 and 3 here. Or we can put molecule 3 and 4 there, and atoms 1 and 2 there, 2 and 4 on the left, 1 and 3 on the right, and 2 and 3 on the left, and 1 and 4 on the right. So this has a total of 6 different ways of arranging things. Now those of you who have had statistics, maybe you recognize this, an equation in order to calculate the number of ways you can arrange things. That would be, let's use again the symbol omega, which by the way some textbooks use W. So we'll use, some people use W, I guess fear of Greek letters. Okay, omega equals in this case 6, but the general case will be n factorial over n1 factorial, n2 factorial, n3 factorial, and n4 factorial. So n here is the total, in this case we're using atoms, total number of atoms. This is number of atoms in the first box. Actually, might as well just do A, B, C, D. Might as well do that to be consistent in our notation. In box A, number of molecules in box B, C, and D. Those of you familiar, n factorial is equal to n times n minus 1 times n minus 2, and so on, all the way down to 1. And also 0 factorial is defined to equal 1. N here is the total number of atoms. There are 4 atoms, so this would be, oops, what am I doing here? 4 factorial. And this is definition, 4 factorial then would be 4 times 3 times 2 times 1. The number of molecules in box A will be 2. That's our constraint. So that would be 2 times 1 factorial is 2 times 1. And also number of molecules would be 2 times 1. Okay, so let's go ahead and see if that calculation works. So for our first constraint, all in A, we have the number of ways of getting that will be 4 factorial. And they're all in A, so this has to be 4 factorial divided by 4 factorial times 0 in B times 0 in C times 0 in D. That's an exclamation point, and that's what that is. We calculate this out. These are all equal to 1, 4. That's just equal to 1. Now let's put 2 in A and 2 in B. Omega for that case would be 4 factorial. We still have 4 numbers. Divided by 2 factorial in A, 2 factorial in B, 0 factorial in C, and 0 factorial in D. And this is equal to 6. All right. Let's look at now, go back to our system here. Now our constraint is we can have molecules in A, B, or C. Okay, so we can have in all 3 of the 4 containers. So that means omega can be equal to 4 factorial. And if we can have it in A, B, and C, A or B or C has to be 1 there, and 2 in the other. So this will be equal to 1 in one, 2 in the other, and then 1 in one. This is just the number of different ways here. 1 in that, 1 factorial, and then 0 factorial in D. This comes out to be 12. And finally, this is the no constraints whatsoever, or sorry, the constraints will be, the constraint will be one molecule there, one molecule there, one molecule there, and one molecule there. Okay, so the constraint is 1 in each one of those. Okay, so the number of ways we can get that is 4 factorial over 1 in the first box, 1 in the second box, 1 in the third box, and 1 in the fourth box. And that's equal to 24. So which has the most entropy? Where all the molecules are confined to be in a particular volume in one box, or whether the molecules can spread out and occupy all the boxes? Well, clearly, since S is equal to K log W, or K log omega, I guess we're using omega, sorry, K log omega, largest omega implies largest entropy, S. So clearly, that has the largest entropy. So when there are no constraints on the system, so none whatsoever, and if you just extrapolate from these to gas molecules, it's more, you have more ways of obtaining a system if you can spread out the gas molecules through the entire volume rather than just confining them into a particular region. So remember in argon and helium example we had before, entropy of mixing, we had argon here and helium here. When we remove this partition, argon now will spread out, helium will spread out, and the entropy will increase. All right. Another way of saying that is when you remove this partition, argon now spread out through the entire volume is going to a more probable state, and helium spread out over the entire volume, as opposed to confined here, is going to a more probable state. All right, so as you go to a more probable state, and a more probable state means that you have many more ways of getting that state, that's more probable, that means that that is the direction of spontaneity. That's where things will go, just out of probability. If something's more probable, yeah, it'll probably happen, rather than something that's not as probable. So it's more probable that you'll have the gas molecules spread out through the entire container that has the largest number of ways of getting it, and since systems tend to go to a more probable state and entropy increases with a more probable state, ta-da! Entropy increases in spontaneous processes where a system goes from a less probable state to a more probable state. And so that's the whole point of the statistical interpretation of entropy. It explains why spontaneous processes happen. Systems just go from a low probability state to a high probability state. They hardly ever go, and we'll find out they never go, practically, from a high probability state to a low probability state. Let's do one more example to illustrate the statistical interpretation of thermodynamics. Let's take a system where you can have 3 energy levels. Let's call this energy 0, energy 1, and energy 2. And we'll have a system consisting of 4 molecules. These are energy levels predicted by quantum mechanics. You remember from introductory chemistry, there's not continuous energy levels for molecular systems, but they're in fact discrete energy levels. We'll learn more about these energy levels in the second part of the course when we talk about quantum mechanics. All right, let's make a constraint, say that the total energy has to equal 0. That's our constraint. What does that mean? The only way to get total energy equal to 0 is to put all 4 gas molecules down here. That's the only way to get that. This implies that the number of ways of obtaining that system, omega, is equal to 1, or the entropy, which is K log omega, that is equal to 0. So constraining all the molecules to be in a particular energy level gives you an entropy of 0. Well, to get all the molecules in the lowest energy state, this implies that you have T is equal to 0, and we'll learn more about that. Temperature equal to 0. So this means at temperature equals 0, entropy is equal to 0. And so we're sort of presaging the third law of thermodynamics, which states that at absolute zero, the entropy of a pure crystalline substance is equal to zero. Now let's make the constraint that the total energy has to equal, let's say 4. So how many ways can you get that? So now they don't have to be in the lowest energy level. They can be in other energy levels. Well, one way to get total energy equal 4 is to put 2 molecules up here and 2 molecules there. Another way to get the energy of total energy of 4 is to put 4 molecules in the energy equal 1. 1, 2, 3, 4. All right, so in this case, omega is equal to 2, or S is equal to K natural log of omega, or natural log, just let's say put a 2 there. All right. So when you remove the constraint that all the molecules have to be in the lowest energy level, entropy increases. So you start at temperature equals 0, absolute 0 Kelvin, the entropy is 0. As you start increasing the temperature, you allow more energy levels to be accessible, and you could rearrange the system many more times when you have more energy levels accessible, so the entropy increases as you increase the temperature. All right, so as I said, we'll have more about this in the third part of the course when you talk about statistical thermodynamics, but I hope I've given you a general idea of how one interprets entropy in terms of the molecular theory.